Everyone. In this video, we're going to get a little bit more practice on quantum numbers and specifically visualizing them. So here in this question, they're telling us we have a contour plot. That's what this picture is of a DYZ orbital. So here's the picture, and if I were to draw this orbital, I just like to show my x-axis coming out of the screen towards you. The y-axis is in the plane of the screen, and so is the z-axis. So if it's in the YZ plane, those four lobes are kind of in the plane of the screen. So that's how I would have drawn this DYZ orbital. So they want us to consider the quantum numbers that could potentially correspond to this orbital. What is the smallest possible value of the principal quantum number n? Well, this one is kind of challenging. I want to think about the allowable values of n and L in this problem. Remember, the allowable values for n are 1, 2, 3, 4, maybe all the way up to 6 or 7. Remember, this tells you the shell in which the electron is located. Or if we think back to our analogy, what building is the electron located in? And just as the number of floors depend on the building, the values of L depend on N. So remember, the allowable values of L go from 0 to n minus 1. So if n is 1, L is 0. If n is 2, L can be 0 and 1. If L is 3, L can be 0, 1, and 2. And if n is 4, L can be 0, 1, 2, and 3. Now remember, L not only has a number, it has a symbol. If L is 0, we call it S. So here's another S. If L is 1, we call it P. So we have S and P. And if L is 2, we call it D. So here we have S, P, D, and F. So getting back to the question, what is the smallest possible value of the principal quantum number n for this orbital? Well, it's a d orbital, and I don't see d orbitals until I get here. So the smallest value of n would be 3. Now, what about part B? What is the value of the angular momentum quantum number L? Oh, I think we already figured that out, right? These are the allowable values for L, and we're saying that when L is 2, we call it D. L is 2. I just wanted to interrupt the video and remind you of that trick that we have to remember the symbols for the quantum number L. Remember, we make a fist. S, P, D, F. So when L is 2, right? S, P, D. When L is 2, you have a d orbital. That's all I wanted to say. And now for part C, what is the largest possible value of the magnetic quantum number m sub L? So we know that L is 2. The allowable values of m sub L depend on the value of L. Just like the number of rooms in a building depend on what floor you're on. So if L is 2, m sub L goes from -2, -1, 0, 1, and 2. So the largest possible value of the magnetic quantum number then is 2. That would be the answer there. So we've answered all of the questions, but I want to just talk a little bit more about these values of m sub L. Notice that m sub L goes from -2, -1, 0, 1, and 2. Remember, the values of m sub L tell you about the three-dimensional orientation in space. So there are how many? 1, 2, 3, 4, 5. 5 possible orientations in space, or in other words, 5 possible d orbitals. And I wonder if we can sketch them. We've already got one d orbital here. Can we sketch the remaining 4? Let's try. So let me sketch my x, y, and z axes, and the orbital here we're showing is in the plane of the screen. It's in the DYZ plane. But couldn't we also have one that's kind of parallel to the floor but perpendicular to the screen? That would be in the DXY plane. Or I'm sorry, that would be in the XY plane. So this would be a DXY orbital. Again, this is an orbital that's parallel to the floor in the XY plane. And a very similar one is still in the XY plane, but it's located directly on the X and Y axes. So again, it's parallel to the floor. This lobe is coming out towards you. This one is called the dx squared minus y squared orbital. So we've gotten 3, right? But we've got 5 possible orbitals because there's 5 possible values for m sub L. Another one that we have here, well, if I have an orbital in the YZ plane and the XY plane, I could also have an orbital in the XZ plane. So this orbital is going to be parallel to your wall maybe and coming out towards you. And then the final orbital that we have is the coolest looking orbital, I think. We call it the DZ squared. It's got density on the z-axis, but then it has that donut. So this is the dz squared. Again, you have 5 possible values for m sub L, giving you 5 possible d orbitals. And again, I forgot to label this one. This one was in the dxz plane. So hope this helps you to visualize quantum numbers. Thanks for listening and good luck.